Let's go over tutorial sheet 1 for organic chemistry. First question here, calculate the degree of unsaturation, which is IHD, or importance of hydrogen deficiency in the following compounds, and suggest 2 or 3 possible structures. Name the functional groups. Alright, starting with the first one, which we have C5H8. Now, how do you calculate IHD? IHD is given by 2 multiplied by the number of carbons plus 2. You are going to subtract hydrogen atoms. You also subtract any halogen, and then you are going to add nitrogen, or those which are in group 5. You don't add or subtract anything, or those atoms which are found in group 6 like oxygen and stuff. And then you are going to divide this by 2. So this is the form that we're going to be using. Now, starting with the first one. So IHD then is going to be equal to 2. How many carbons do we have? We have got 5 carbons, and then plus 2 hydrogens. We have got 8 divided by 2. So what is this going to give us? We have got a 12 minus 8 over 2. That is going to give us a 2. Now, when we have got IHD of just 1, it means that we either have one ring or we have got one double bond. If we have got IHD of 2, it means we can have one ring, and in the same ring we also have a double bond, or we can have two double bonds, or we can have two rings for that compound. So all those are meanings of IHD. So what are we saying? Either two double bonds, or I have got two rings, or I can have a ring and a double bond combined, or I can have only a triple bond. A triple bond has got an IHD of 2. Now, for this one, since we can see it has got C5H8, what are the possible structures which are able to draw? Because the IHD is 2, it means we can have a structure with a ring and a double bond. So this is 5 carbons. I can write a pentagon. And then just at any point I'm supposed to put a double bond, and they should balance with the formula. We've got 5 carbons, but are there 8 hydrogens? So this point has got 2 hydrogens, 2 hydrogens, 2 hydrogens. This one is just 1, this one is also 1, because we have got a double bond. That balances. We have got 8 hydrogens. Another thing that I'm able to do is I'm able to draw a compound with 5 carbons, 1, and this should be linear, 2, 3, 4, 5, but it should have 2 double bonds because of the 2 IHD. So here I can put another one there. Let's find out how many hydrogens are here. So at this point we have got 2 hydrogens. Here we only have 1. Here we have got 1. Here we have got 1. And then at the end here we have got 3 hydrogens. So this has balanced. Another, you can have 1, 2, 3, 4, 5, and then a triple bond at any point. So this is still IHD of 2. So we have got 3 hydrogens here. We have got 3 hydrogens here. We have got 2 hydrogens at that point. Where else? Okay, how many hydrogens do we have here? So we don't have any hydrogen. What of here? We don't have any, because those carbons are fully occupied. So this is still balancing the 8. So that is for the first one. Let's look at the second one. The second one, we have C10H20 and then O2. What would be the IHD for this one? So using the same formula that we already have here, IHD then is going to be equal to 2 times the number of carbons, which is 10, minus number of hydrogen, which is 20. Now oxygen doesn't affect IHD, so will not include it, divided by 2. So this is 2 times 20, which is just a 20, and then minus 20. Okay, I've forgotten a 2. Remember, it's supposed to have a plus 2 there. So that is 22 minus 20, which is a 2 divided by 2. That is going to give us a 1. So we have got IHD of 1. What does this mean? IHD of 1 means we can either have one double bond or one ring. Now we have got 10 carbons in this molecule. So if I've got here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have got two oxygens. I can have oxygen with a double bond at this point, and then I put another oxygen here. Now this oxygen should have an hydrogen, meaning that I've got the carboxylic acid functional group. Well, for the previous one I forgot. The question is saying name the functional group. For the previous one, we had a cycloalkene. We also had an alkene, just a linear alkene, and also an alkyone. Those were the functional groups. So for here, this functional group is a carboxylic acid functional group, IHD of 1. Why? Because we only have one double bond with the oxygen. If you want, you can calculate the hydrogens that are supposed to give you 20. What can be another structure for this one? Well, I can have one carbon, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let me have oxygen at this point. Let me have oxygen. Okay, if I put the double bond, that will mean I'm going to increase IHDs. So let me put one oxygen here with an hydrogen. Let me also put one oxygen here with an hydrogen. So what functional groups are these? These are alcohol functional groups. Now we don't have any double bond here. Okay, we don't have any double bond. So what do? I can put any double bond at any point, and then I've covered for the IHD. And if we count the number of hydrogens or all the atoms, supposed to add up to what we have at that point. What other structure am I able to write apart from this? So I've written the one with a carboxylic acid functional group, the alcohol functional group, and alkene. We have got alkene and alcohol here. So I can have another one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 carbons. Now another functional group I can either write it at the end, one oxygen, and then I can put another oxygen with an hydrogen here. So this functional group is a ketone. Carbonyl at the end is a ketone. Carbon with a double bond with oxygen. Or I can put this functional group at any point on the middle, then it's going to be an aldehyde. So this double bond is the one covering for the IHD, and then this OH, I'm just putting it there because we have got two oxygens. All right, so that is going to be for this one. And then the next, C7, H11, and then N. What would be the IHD? So IHD in this case is going to be 2 multiplied by 7 carbons plus 2 minus, we have got 11 hydrogens. Remember nitrogen we add, so plus 1, and then divided by 2. 2 times 7 is 14 plus 2, that is 16 plus 1, 17 minus 11. That is going to give us a 6 divided by 3. That is going to give, divided by 2, that is going to give us a 3. So IHD of 3, what does that mean? We can either have a triple bond or we can have, now, when we have got IHD of 1, remember, it can either be one ring or one double bond. When we have got IHD of 2, we can have two rings, or we can have two double bonds, or we can have one ring and then one double bond, or we can have just one triple bond. Now, when we have got an IHD of 3, it has got a lot of meanings. It is either we are having three rings. Apart from that, we can also be having three double bonds. Okay, we can also be having a combination of a ring and a double bond. How is that? We can have two rings and one double bond, or we can have two double bonds and one ring, or we can have two double bonds. Two triple bonds. So all those are going to be the meaning of that IHD. Now, apart from having, sorry, I said two triple bonds. I can have one triple bond and then one double bond like that. Because one triple bond means we have got IHD of 2. And then that other one IHD which has remained, we can put a double bond or a ring. Okay, so that is going to be the meaning. Now in this one we have got 7 carbons. How do you go about it? Well, the first one I'm able to write 1 carbon, 2, 3, 4, 5, 6, 7. So what should be the first thing I should write? Of course, we are taking note that there is a nitrogen. So this carbon which is at the end, I can put a triple bond with that nitrogen here. If I put a triple bond, that is, I've used two IHDs, meaning I've remained with one IHD. I can just put one double bond at any point. What functional group is this? This is called a nitrile functional group. So we have got a nitrile, which is carbon triple bonded to a nitrogen, and then we have got an alkene, functional group of an alkene, that's a double bond. What other structure am I able to write? Let's have again 7 carbons. 1, 2, 3, 4, 5, 6, 7. But I can have a nitrogen with two hydrogens like that. I have not put any double bond here, meaning that I have not used any IHD. Meaning I can, in this molecule, I can either put two double bonds at any point, okay, S- not really two, but I can put any three double bonds. So I can put here, here, and here. This is one IHD, this is one IHD, this is one IHD. Or I can remove this one and then put a triple bond here, because triple bond is two IHDs, double bond is one IHD, giving us three IHDs. So this is another possible structure that I'm able to write. What is the functional group which is present in this compound? NH2, we call this amine functional group. So when the IHD, when the amine is together with the carbonyl, which is CO, it will give us amide functional group. Right. Let's look at the next question. So for the next, we have got C8H10Cl2. What is going to be the IHD? So then in this case, IHD is going to be 2 multiplied by 8, subtract 10, and then add a 2. And then we have got chlorine. Chlorine, these are halogens, and there are the two of them. So we're going to subtract and then divide by 2. So we say this is going to cancel. 2 times 8 is 16, minus 10 is 6, divided by 2. That is going to give us a 3. So in this molecule, just as we said earlier, IHDO3, meaning we can have 3 rings or 3 double bonds. What's the other meaning? We can have a combination of double bond and ring, or we can have one ring and a triple bond, or we can have one triple bond and one double bond. Now we also have chlorines here. So one structure I can write, we have got 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I can cover the IHDs with just double bonds. I can put any three double bonds. 1, 2, 3. We should also have the chlorines. I can put chlorine here and then another chlorine at any one point. So this one, if we can count the hydrogens to make sure that they are balanced. At this point, we have got two hydrogens. At this point, we only have one. We have got one. We have got one. We have got one. We have got one. Even here we have got one, and then here we have got two. How many hydrogens are these? 2, 3, 4, 5, 6, 7, 8, 9, 10. Balanced with the 10 that we have. What other structure are we able to write? I can again write 1, 2, 3, 4, 5, 6, 7, 8. Now we are remaining with putting, to make sure that we cater for the IHD. I can put a triple bond at any one point and then a double bond, and then just put the chlorines at any point. I can't put chlorine here because this carbon is already balanced. So I can put the chlorine here or any other point. Another I can write is I can write a ring. Now this ring has got 6 carbons, meaning I've covered one IHD. I can put chlorine here, I can put chlorine here. I'm remaining with two IHD, so I can put a double bond here and a double bond here. So this is also going to have an IHD of 3. So for this question, this is how I'm able to approach it. Let's consider the next. Provide an explanation for the following observations. The boiling point of cis-2-butene is higher than that of trans isomer. So let's write cis-2-butene. We have got like this. And then, so this is the cis because the methyl groups are on the same side. And then the trans is going to be like that. The methyl groups are on opposite sides. Now, why do we think the cis-2-butene is having a higher boiling point? So this one has got a higher boiling point than this one. So this one has got a lower. So this has to do with the polarity of the bonds. If we look at the dipoles, okay, if we look at the dipole, we have got a double bond here, and then we have got the carbon atoms at these two ends. So what you are going to be able to see is that when you're talking about a double bond, what do we know about the double bond? Does it give us electrons or it does take electrons? So from our reaction mechanisms, when we are referring to a double bond is actually a nucleophile. What does that mean? It loves the nucleus. So then, if it loves the nucleus, what does, okay, I've said it loves the nucleus. What something that loves the nucleus, what does it really do? So if something loves the nucleus, it means it attacks the nucleus. In other words, it has got some electrons which are able to attack the other compound. So in this case, this carbon here and this carbon here, I mean these bonds which we have here, what we are going to see is we are going to have a dipole. Okay, so because we are saying the double bond has got some electrons, so a dipole more goes in this direction from the double bond. Also, a dipole is going to go in that direction from the double bond. And then what is going to happen because of that? So from our vectors, we know that if we have got a vector going in this direction, it has got components, one component in this direction, one component down. If it is going in this direction, one component will be down, one component in this direction. So these two components will cancel each other. And then these two are going to add up. So the cis isomer has got a net dipole going in this direction. But for the trans, we are going to have a dipole in this direction, a dipole in this direction. So these two will be able to cancel each other. So that the cis has got a net dipole. Because of that net dipole, that makes the bonds more strong such that if you want to boil, you have to give it more energy. That is why the boiling point of the cis isomer is higher than that of the trans isomer. Now, if we look at the which one is more stable for the next one, we have got trans 2-butene and the cis 2-butene. Which one is going to be more stable? About stability, the trans is more stable than the cis. The reason is these two groups are on opposite sides. So we have got what is called the steric hindrance. So steric hindrance just has to do with the spaces which these two have occupied. This methyl has got electrons. This other methyl has got also electrons. So if those electrons are near each other, they are going to be repelling each other. And so that will make the molecule not to be stable. So that is why this one, because of the repulsion due to steric hindrance, the electrons which are found in those bonds in the methyls, it is not going to be stable in comparison to the other one. Let's consider this one. Rank the following groups in the order of priority, beginning with the lowest priority. Now, basically, this is applied when we want to name a compound either being S or R. Let's say I've got a carbon, it is bonded to a bromine like that, and then it has got, let's say, an alcohol functional group, it has got CH3, and then it has got an hydrogen. Which one is going to be group one? I mean, the first group, the second, the third, and the fourth, for us to be able to determine the RS configuration. So what you do is you consider the element that is direct linked to the central carbon or the chiral carbon. So in this case, you consider the molar mass of that element that is direct linked. So this one, definitely hydrogen has got the lowest molar mass. It will always be the first. group. Okay, this is going to be the lowest group. And then if we see here, it is the carbon which is direct link. This dash is just showing that is where we are bonding to the first or the chiral center. So this carbon is the one direct linked. Even this one, we have got a carbon. So go to the next atom. We still have, now you consider those atoms with the highest molar mass. The next is this one. You saw you are now considering those atoms which are bonded to this carbon. So we have got this carbon, even here I've got a carbon. And then if you continue considering this one, the carbons are done. But to this carbon, there's also this carbon. So this one is going to be more stable. I mean, it is going to receive a smaller priority, or is going to have a higher priority, let me say, in comparison to this one. The thing is this, when I want to see which one has got higher priority, I have got carbon bonded to carbon, and then hydrogen, hydrogen, all these others are hydrogens, and then I've got another one, carbon, 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 and then all these others are hydrogens. So if this is the carbon which is direct linked, is even this one is the carbon direct linked, in this case I can't choose which one has got a higher priority. Why? Because they're both carbons that have got the same molar mass. Go to the next atom which is linked to this same carbon, which has got higher priority or higher molar mass. Here we have got a carbon, still here we have got a carbon. They are the same, I can determine. Go to the next. Now for this one, the next I can go to is only hydrogen, but for this one I'm going to a carbon, meaning that this one has got a higher priority than this one. So meaning that from hydrogen, the next is going to be this one, followed by this one. Now bromine is going to be the one with most priority. Why? Because it has got the highest molar mass in comparison to these others. We are not considering the molar mass of the whole compound, but the molar mass of an individual atom linked to the chiral carbon. Let's consider this other one which is down. So the list, all of these. Okay, for this one, you can see oxygen is the one which is direct linked to the chiral carbon, meaning that this is going to be the one with highest priority, the fourth group. For the others, we have got carbon first linked, carbon first linked, carbon first linked. So meaning they are the same. Go to the next, oxygen, oxygen, hydrogen. So meaning that this is going to be the first with the lowest priority, because just after the carbon, okay, just before the carbon, actually I've got an oxygen which I didn't just say. So I've got this oxygen, meaning that after the carbon, all of them, the carbon is cancelling out because it's the same. After the carbon, the oxygen will still cancel out because it's the same. After that, for this molecule which is here, the only atom which I have left is an hydrogen, meaning that this one is going to win priority. But these two, they still have oxygens. After the oxygens, this one has got an hydrogen, meaning that this is the one which is going to follow because it has an hydrogen. But this one has got a carbon. Carbon has got a higher molar mass. So this is going to be the third group. So the first is this one, second, third, and then the fourth is hydroxide. Let's look at the next. Of course, bromine, it has got a higher molar mass from what we know from the periodic table. If we did check on our periodic tables, meaning that that should be definitely the last group, the bromine. Okay, now let's identify the first group. Chlorine has got also higher molar mass and this direct link to the chiral carbon. Let's consider this carbon. So this is a carbon, this is a carbon. Okay, meaning that we can't determine at that point. And then look at the elements which are direct linked to the carbon, which have got higher molar mass. So I've got a bromine and a chlorine. So which one has got a higher molar mass between the bromine and the chlorine? So chlorine has got a less molar mass. So meaning this is going to be group 1. And then group 2 is going to be this one, which also has a carbon. And then group 3 is going to just be the chlorine itself. And then group 4 is going to be this one. Okay, so that will be the order of priority. Now for the next one, 4. The first one we are going to identify with the least priority. I can even draw out these atoms are direct linked. So we have got a carbon bonded to another carbon, and then it has got three hydrogen. For the hydrogen, I'll just put these dashes, and then here this is where we're connecting our group. And then for this one, we have got a carbon double bond with a carbon that has got only two hydrogens. And then for the other one, we have got a carbon with three methyls, meaning I've got a carbon like this. Also here I've got a carbon like that. So here I've got a carbon like that. For the other one, we have got a carbon, only two methyls, so like this. And then maybe on top like that. And then the other one is an hydrogen. So to this carbon. And then the other one, we have got carbon, 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 carbon. And then the other are hydrogens. So which one is going to be the first lowest priority group? So all of them have got carbons. So if I cancel the first carbon, I'll cancel the first carbon, cancel the first carbon, cancel the first carbon, cancel the other carbon. The next carbon linked, the next atom linked to the carbon which is direct linked to our chiral center will also cancel like that. Now, if we consider this one, the next that we are going to be having is going to be what? They are just hydrogens. All right. They are just hydrogens. Even for this one, they are just hydrogens. So I'll just now consider this one and this one because what follows are just hydrogens. If we start cancelling the hydrogen, this will cancel with this will cancel with this will cancel with this will cancel with this. But this one has remained with one hydrogen, meaning that this is going to be the one with the least priority, followed by this one. Why? Because one is going to have a higher molar mass in comparison to this one. And then now we can come to these others. Okay, remember we had cancelled first those we started with, but for this one, this carbon can also cancel this carbon. Here we have got hydrogen, here we've got carbon. Carbon has got a higher molar mass, meaning that the next group which will follow is this one, and then this one will follow. This one has got a lot of carbon, so this is going to be the group of highest priority. So that is how we are able to determine for this one. Question number 2. Write the 2D or 3D stereochemical formula and give names using EZ designation for the isomers given below. We have got 2 bromo, 4 chloro, XZ, 2 in, 5 in. So just writing the formula of this one, what is important is the XZ. What can we tell from that? X means we have got 6 carbons. So carbon number 1, number 2, number 3, number 4, number 5, and number 6. But this tells us that at position number 2, we have got a bromine. Or let me start with the functional groups. Okay, the functional group. 2 in means that position number 2 we have got a double bond, the in. So this is 1, 2. So here I've got a double bond. Position number 5 we have got a triple bond. That's the in. 1, 2, 3, 4, 5. So here I've got a triple bond. And then we have got 2 bromo. The 2 is here. So we have got a bromo here. And then 4 cyclo-X. At position number 4 I've got a chlorine. 4 chloro, not cyclo. 1, 2, 3, 4. So we have got a chlorine here. Okay, so this is a structure. Now the way I've drawn it, are we able to determine the E or the S? So what I'm going to do is on the double bond, let me write it. I can put it like this. I'll put the double bond like this. And then here we can have the chlorine like that. After the position where the chlorine is, we still have another atom like that. And then we have got a triple bond. And then this side, just at this point, we have got a bromine like that. So what you do is on the double bond, you are going to cut in this way. So we are going to consider the groups this side and this side. Now, even if I have not shown, it means that at this point, I've got an hydrogen, even if I can't see. This one is a methyl, which is here. So I'm going to consider if these two, this side are the same, then this compound is not going to exhibit the E or Z isomerism. So what you do is you consider which one has got a higher molar mass this side, which one has got a higher molar mass this side. So here, the one with a higher molar mass is this one. I'm going to give it 1. And then coming down, The, or let me cut it on the middle like this so that it will be easier. The one with higher molar mass is this group which is down, so I'll give it position 1, meaning that this one has got a lower, this one has got a lower in comparison to this other one. Because carbon is 12 plus 3 hydrogens, which is just about 1. That is going to give us 15. Bromine is much higher. So when these two groups with different molar masses are on opposite sides, we give this as the E isomer. So then this one I've drawn here is going to be E. So just this same name, just in front, I'm going to put E and then I write 2 bromo and everything just the same. But had I written this group on top here and then this hydrogen down, this group with highest molar mass would have been on the same side with the bromine. In that case, it would have been Z. Okay. So in a case when you're talking about this, what's the difference between the EZ configuration and the trans and cis? So for the trans and cis, if one group is the same, let's say this group and this group, these two groups which are on opposite sides, they are the same. Then we can also use cis and trans. But if you're just talking about the molar mass or those groups on opposite sides, that's when we talk about the E and Z. What are the next? So remember, we can either draw the 3D or the 2D. The one I'm from drawing, that is the 2D. Now for this one, I've got 3 chloro, 1,4 hexadiene. So this is hexa, meaning 6 carbons. Number 1, number 2, number 3, number 4, number 5, number 6. At position number 1 and 4, we have got double bond. So we have got here double bond 1, 2, 3, 4. Even here, I've got a double bond. And then at position number 3, we have got a chlorine 1, 2, 3. So a chloro here. So I can also write this like this. We have got a double bond here. And then I can take it down like that. So 1, 2, 3. I can come like this 4, 5. I can do like there 6. Okay, 1, 2, 3, 4, 5, 6. Now at position number 4, I've got another double bond 1, 2, 3, 4. So I've got a double bond here. Now for here where I'm getting the double bond, let me write it straight. 1, 2, 3, 4. Okay, 1, 2, 3, 4. Can I just change this one so that I'm going to put it? I can have it like this. Okay, just the same way I wrote it, it's okay. Position number 1, number 2, number 3, number 4, 5, 6. It doesn't matter where the direction I go. Depending on the direction I'll go myself, that will determine the name I'm going to give it. So this is where I'm going to have the double bond at position number 4. Now, considering here at position number 4, where do we have the chloro at position number 3, 1, 2, 3? So I've got a chloro here, Cl. What element is going to be at this point? We only have an hydrogen here. And then even here we only have an hydrogen. I'm just putting there so that we can see how the name is going to be. Now in this case, also here we're going to have only an hydrogen. Okay. Now at this point, we also have only an hydrogen because we don't have anything else this side, even here an hydrogen. Now because these two are the same, I'm not going to give the EZ configuration for this double bond which is here. We will not give it. But for the other double bond, we can give it. Okay, because this group, these two groups which are here are different, and then these two groups are different. So if I cut this on the middle like this one is going to be position number 1 because it has got a higher molar mass. This is a methyl group, this is a hydrogen. And then this is going to be position number 1 also because it has got a higher molar mass than this hydrogen. And these two are on opposite side, meaning that this is going to be the E isomer also. Why? Because I put them on different sides, but had I put them on the same side, it would be Z. What are the next? 3 isopropyl, 2 hexene. Okay, 1, 2, 3, 4, 5, 6. At position number 3, we have got isopropyl 1, 2, 3. Isopropyl, this is the functional group. And then 2 hexene, meaning at position number 2, we have got the double bond. So here, okay. Now I can write this like this 1, 2, and then I'll put a double bond like this. and then I can have this group down like that, and then on top I'm going to have 1 2 3. Okay, 1 2 3 4 5. This is 6 carbons. I've just made it into a 2D shape like that. Of course, we have got an hydrogen even if we can't see it. So if I cut this on the middle like this is going to be the first group because it has got a higher molar mass than the hydrogen. What of this side? We have got the isopropyl, and we have got what of this group, which is what will be the name? It has got 1 2 3 carbons. This is a propyl. This is an isopropyl. Which one is going to receive the first number? Because this is basically having the same molar, I mean, having the same number of carbons in that case. Now, how many hydrogens does each one of them have? This one, the first carbon here has got 3 hydrogens. This one has got 2 hydrogens. This one has got also 2 hydrogens. What of here? This carbon has got 3 hydrogens. This carbon has got 3 hydrogens. This one has got only one. This is 7, and then both are 7. So they are all having the same molar mass. So such a configuration like this one, from some reading, if you have got the same molar mass like that, this is going to be given as Z. Like basically you have got something with the same molar mass on the same side. You are going to give it like Z. Because if I took this one as position 1 with this one as position 1, this is going to be the Z isomer. But if I took this one with this one, it would be E isomer. Now, because these ones have got the same molar mass, let me just take it as Z, considering the one which is down. 3-methyl hexa 2,4 diene. This is also hexa 1 2 3 4 5 6. At position number 3, we have got a methyl. So here we have got a methyl. Hexa 2,4, position number 2, we have got double bond 4, we have got a double bond. Okay. So I can write this as 1. I'll put it like this. Let me have the methyl down here, and then the group is going to continue 4. I'll put it like that. Number 1, number 2, number 3, number 4. There is a double bond at number 4. And then let me have it up like that. This is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. So even if we can't see there is an hydrogen here, there is an hydrogen here, there is an hydrogen here. This is a methyl group at this point. Even this one is a methyl group. So if I cut at this point, this is going to be position. This is going to be group 1 on this side, and this is going to be group 2 on the other side. So meaning that for this part at position number 2, this is going to be E. And then for this other one, if I cut also on the middle like this is going to be the first group, and then this group which is down is going to be a second. I mean the first also, because it has got higher molar mass than the hydrogen. Meaning that at position number 4, we also have the E. So for the name for this one is going to be 2E, 4E, and then we name 3-methyl hexa 2,4 diene. That is going to be the name. Let's consider the next. Write the name of the following 2D structures. Include the pertinent stereochemistry in the name. Want to also include the stereochemistry. So if I put an hydrogen here and then an hydrogen here, I also put an hydrogen here. This is going to be the first group. This is going to be the first group. They are on opposite sides, as we are able to see. Opposite sides. What is going to be the name? This is position number 2. Okay, this is going to be 2E. And then at this point, this is going to be the first group. This is going to be the first group also. They are on the same side. What is going to be the name? The name for this one is going to be, this is position number 4. That is going to be 4Z. Now, let's give it a name. How many carbons does this molecule have? If I started counting from this side, this would be 1, 2, 3, 4, 5, and 6. If I started counting from here, this would be 1, 2, 3, 4, 5, and 6. Now notice that if I start counting from this direction, the first double bond is at position number 2, same if I started counting from the other direction. But if I start counting from this direction, the methyl is going to be position number 3, and then the other is going to be position number 4. So I would rather start in the direction that will give me a lower number to the methyl. So then the name is going to be 2E, 4Z, and then this is going to be what? At position number 1, position number 2, I've got, oh, sorry, let me first name the methyl. So I'll save 2E, 4Z, 3-methyl. When you separate a number and the letter, use a dash. And then at position number 2 and 4, I have got double bonds. I can write 2, 4 hexadiene, or I can say hexa 2, 4 diene. Or I could have written 2, 4 hexadiene. So either way that we want. And then for this other one, if I start counting from here, it should be 1, 2, 3, 4. If I start from here, 1, 2, 3. So I'm going to start from the direction that will give me a lower number to the methyl, because if the other groups are basically on the same position. So there's going to be a hydrogen here, there's going to be a hydrogen here, hydrogen here. So at position number 2, is this going to be E or Z? Can see the first group is here, the first group is here, they're on the same side, so that is going to be 2Z. What of this one? First group is here, first group is here, so that is going to be 4Z. So they are basically on the same sides. So that is going to be 2Z, 4Z. And then at position number 3, I've got a methyl. So basically the name is the same. 2Z, 4Z, 3-methyl hexa, 2, 4 diene. What of this other one? This would be 1, 2, 3. Sorry, 3 is here. 4, 5, and 6. This is going to be the hydrogen. Let me remove the numbering. We already know the direction we are starting from. This is going to be a hydrogen, and then a hydrogen. These two groups are on the same side. Then at position number 2, this is going to be E. What of here? So basically this one and this one, why am I even naming? They are the same compounds. Let's check. Are they different? So it is the same compound. Let's name this one. So for this one, depending on the direction I number from, this is going to be 1, 2, 3, 4, 5, 6. I always need to make sure that I cover the double bond in my numbering. So the name of this one, let's look at the groups. This is going to be, which one is going to be the first one? Which one is going to be the second one? So these two are basically on the same side, and they are the same. They are both methyl, so we are not going to have any E or S on this one. Why? Because it has got the same groups. In other words, this portion here is not having 4 different groups, or let me say different groups if I cut like this, because if I say 4, a double bond can't have 4 groups. And then if I come to this one, this is going to be the first group. If I cut on the middle like this is going to be the first group. They are on the same side, meaning that this is going to be a Z. Okay, so then what is going to be the name? The name is going to be, let me remove this. So we have already seen for the other one that we are not going to name the first part, but for the other one here, the groups are on the same side. This is going to be Z. I'll just say Z. Position, let's put the groups first. If this is 1, this is 2, 3, 4, 5, 6. Position number 2, number 3, and number 4, we have got methyl. So 2, 3, 4, trimethyl. And then we have got, this is going to be hexa. Position number 2, we have got a double bond, position number 4, a double bond, and then diene. So that is going to be the name for this one. Okay, let's consider this one. Which one is Z or E isomer? You can try to check out if you are able to answer that one within a minute and then come to check out the answer. Alright, so we're going to check which group has got the higher molar mass if I cut on the middle like this. So this portion, this one is going to have a higher molar mass because carbon is 12 plus 3 hydrogen, that is going to be 15. And then the other side, this is going to have a higher molar mass, and they're on opposite sides, so this is going to be E. What of this one? So if I cut again on the middle, this is going to be the first one, and then coming down, this is going to be the first one. Opposite sides, that is still E. And then for this one, we have got a carbon here and then bonded to chlorine. This is going to be the first group, and then this is going to be the first group. So same side, this is going to be Z. And then for this one, where the double bond is, the double bond is here. If I cut like that, we have got nitrogen, hydrogen, and then we also have the, okay, let me do this. This group is basically the same as this one, a carbon, same with the carbon here, but oxygen has a higher molar mass than the two hydrogens, meaning that the group which is down has got a higher molar mass. So this is going to be 1. Now for this side, if I go in this direction, I'm going to find this group faster than going in this direction, meaning that going up, this side is going to have higher molar mass, that will be 1 than going down. Okay, so meaning what is going to be the name? Is it Z or E? Opposite directions, that is going to be E. Consider 2-methylbutane, which is also called isopentane, citing along the carbon 2 carbon 3 sigma bond. Draw a Sawhorse formula and convert it into a Newman projection. Now first thing first, okay, this one is 2-methylbutane. Butane, we have got 1 carbon, 2, 3, 4. At position number 2, we have got a methyl. So it is like this. So this is carbon number 2, this is carbon number 3, and we want to look through this bond. So how do you want to look? You want to put your eye at this point, such that when you look at this carbon, you'll not be able to see this other carbon in this direction. So in that case, I can also write this as we have got a carbon, another carbon, another carbon, another carbon. And then here I've got a carbon with 3 hydrogens. And then I've got hydrogen here, I've got hydrogen here, hydrogen here, hydrogen, hydrogen, also here. And also here I've got 3 of them. So to write a Sawhorse formula, I'm taking this carbon and this carbon. How am I going to write that? I'm going to write 1 carbon here, that is a carbon number 2, and then write like this. This is carbon number 3. Now on carbon number 2, you can see a methyl on top. Let me write a methyl on top like this, CH3. And then we can see uh, also a methyl this side, this methyl. Okay, just on carbon number 2. This is carbon number 2, this is carbon number 3. So to carbon number 2, I've got 2 methyl. So I'm going to put another methyl here. And then the other one is a hydrogen attached. And then to the carbon which is at the back, I have 1 methyl and then 2 hydrogens. So if I put that methyl on top, the 2 hydrogens are going to be like this. Okay, like that. Meaning that these 2 on top are on the same, like you are able to see them straight like that. Okay. Now, this is a Sawhorse formula. I want also to write a Newman projection. So let me go on the next page and just show what I've done. This is carbon number 2, and then I've got carbon number 3. I can have, let me have the 1 hydrogen here, and then the 2 methyls, let me put them in this direction. This is basically the same thing. And then for the other one, we add one methyl. Let me have that methyl on top like this. Should I? Okay, to make it just more simple, let me put the methyl group down. It doesn't matter. CH3, and then the two hydrogens, let me put them like this. So meaning if I look through this direction straight, my eye is at this point. What am I going to see? I'm only going to see this carbon. I'll not see the carbon which is at the end. So we have this carbon. On top, we have got hydrogen. And then I've got a methyl this side. And then I've got another methyl this side. The other carbon which is at the end, I can't see it. So we'll use a bigger circle like this, though we can't see that carbon. And then at this point, we are going to see that hydrogen. At this point, the other hydrogen, and then down we are going to see the CH3. Okay, so this is, I've converted this formula to the Newman projection. So this is actually called the staggered configuration because these groups which are behind have not been covered by those groups which are in front. But in a case like this one, you can see these groups behind, they've been covered, all of them. So this is called an eclipse configuration. Now, draw, okay, P, using the energy cost given below, which are these ones here, plotted the potential energy versus degree of rotation about C2, C3 sigma bond graph. Now, we have got an eclipsing interaction, meaning that if I have got this kind of arrangement, we have got CH3, CH3 making an eclipse, meaning they are covering each other, there's going to be a repulsion of giving us about 11 kilojoules per mole. But if it is a gauge interaction, what do we mean by gauge interaction? It is like this. This interaction between these two, they are staggered. The angle between them is 60 degrees. Such an interaction for a carbon 3 to carbon 3, the energy is going to be giving us is 3.8, meaning that the repulsion is not that much high as when they are eclipsing. And then for a CH3 to hydrogen, the energy is 6 if they are eclipsing. What do we mean like that? This eclipse here, that's the energy that is going to give us 6. But if it is that is hydrogen to hydrogen, it is 4. But if it is CH3 to hydrogen. Let's say this CH3 which is here was at this position for hydrogen. This is the energy it would give us, meaning that there is more repulsion for the CH3 to hydrogen. Why? Because the CH3 has got a lot of electrons, and so there will be more repulsion in the hydrogen other than just the hydrogen with another one of its kind because they've got fewer electrons. Now, for the gauge interaction between the hydrogen and hydrogen, or the CH3 and H, there's basically no energy. What do we mean? Here, there's basically no repulsion there. It is stable like that. Meaning that when I get to put this group so much near to this one, there's going to be instability. Okay. So what does that tell us? So I'm able also to make some diagrams here before even draw the potential energy diagram. So here I've got two gauge interactions. And remember, each one of these gauge interactions from what we're able to see is 3.8. So what I have is 3.8 plus 3.8. What will be the energy that I'm going to have? That is going to give me 7.6 in this molecule, kilojoules per mole. Now, what happens if, let's say, this CH3, I make a swap, this CH3 comes here, and then this hydrogen comes here, meaning I've rotated that molecule. So I'm going to maintain the position of these others. And then I'll simply change. I'm going to have hydrogen here, and then I've got the CH3 here, and then I've got the hydrogen here. Now for this one, the only gauge interaction that we have between the CH3 molecules is this one, meaning that the only energy in this molecule is the 3.8 kilojoules per mole. What does that mean? This means that this molecule is more stable than this one. Okay, so these are the possible molecules that we're able to have. Again, I can have this CH3 which is here being this hydrogen, but it's going to have the same energy as this one. Okay, So these are the possible staggered configurations that we're able to have. What are the eclipse configurations? Now for the eclipse, I'm going to keep the one on the middle the same way it is. We have got hydrogen here. I've got a methyl this side. I've got a methyl this side. And then we are going to have like this. If I take these groups, these ones which are at the back, this CH3, let's say I bring it here. Okay, it has been eclipsed. It's behind us, and now I'm just putting it there, though we will not be able to see it. And then the other hydrogen, which is behind there, and then the other hydrogen is behind here. Now, we've already seen the energies. The CH3, CH3 eclipse, the energy is giving us is 11, and then CH3 to H is 6, H to H is 4. So meaning what? CH3 to CH3 here we have got 11 kilojoules per mole. H to H eclipse is 4 kilojoules per mole, and then CH3 to H, this is 6 kilojoules per mole. So what is the total energy in this molecule? 11 plus 4 plus 6. This should be able to give us a 21. Another possible molecule that I'm able to draw for this one is I can have this CH3 making an eclipse with this hydrogen. Okay, this is kilojoules per mole. So we are going to have a hydrogen on top, CH3 this side, CH3 this side, and then we are going to have like that. Let me have now this molecule being behind here, and then let me have now this hydrogen being here, and then the other hydrogen being here. Now here the kind of, we know that H to CH3 eclipse, the energy for that one is what? 6 kilojoules per mole. And then H2CH3 is also 6 kilojoules per mole. Also, this one is 6. So this is going to give us 18 kilojoules. So what does this mean? This one is the most unstable molecule having the maximum energy, and then followed by this one, followed by this one, and followed by this one. So where the CH3 got interaction is only one, that is going to be the minimum energy. So this is what we are going to see. Okay, so the minimum energy, we have got this point, which is the CH3 interaction. Okay, the CH3 and the CH3 interaction is a bit or small, and then it is the same as this molecule. The maximum energy we saw when these two groups were together, which is the same as this one. So take note of also just the angles. When you rotate the 60 degrees, it is continuing to change like that. Now I'm just wondering why this angle here is 0 degrees. Otherwise, if you consider these two, for the eclipse, the angle between these is not there actually. So that is, you consider it 0 degrees. Okay, so that is how you get to take. Now the questions are still there. Draw and conformational Gauche conformation and two different eclipse conformations. So we have actually already done this. So for the anti-conformational just means that these two groups are on opposite sides. Okay. When I've got a CH3, where is that molecule? Let me show that. If I've got a CH3 here, CH3 here, they are on opposite directions. That is the anti-conformation. And then the gauche means that this CH3 is next to the other one, like here. Okay, they are next to each other. That is the gauche conformation. And then the other one and two different eclipse. So the eclipse you can draw any, either this one or this one. Draw the least stable conformation of isopentene. Isopentene is the same as 2-methylbutane. We've already drawn that. Which conformation has the maximum torsional bar? The maximum torsional bar is the one which has got maximum hindrance, which is this one actually, the 21. Okay, so that is it for that question. Assign the R or S configuration at each chirality center in chlorophynical, a broad spectral antibiotic. So we want to assign at every chirality center. So we have got this one as a chirality center. Look at the groups which are on this one. We can't see the fourth group, right? We only have see three things attached to this one. So to consider which one is going to be position number one, this is going to be position number one. Why? Because oxygen is directly linked to that carbon. What of position number two? This is a carbon, this is a carbon, so we can determine that. Go to the next. There's a carbon here, there is a nitrogen here. Nitrogen has got higher molar mass than carbon, meaning this is going to be group 2, and then this is going to be group 3. The fourth group, though we can't see it, there is an hydrogen which is hidden. Since the OH is in front, the hydrogen is going to be at the back. So to name the configuration here, we move from 1 to 2 to 3. Since already the hydrogen in the back, if you go clockwise, this is towards the right, so this is going to be the arrow configuration about this carbon. If you consider again at this point, we have got a nitrogen, we have got a carbon, we have got a carbon. Since this is a nitrogen, it has got higher molar mass, is going to be position number one. You don't consider molar mass of the whole group, just the molar mass of the carbon direct linked to this carbon. And then this is a carbon, this is a carbon. This one is linked to oxygen, this one is also linked to oxygen. Okay. This one has hydrogen as one as also hydrogen. This one still has another carbon linked. So meaning this is going to be position number two because it also has another carbon. And then this is going to be position number three. Where is position number four? We have got an hydrogen, though we can't see it since this group is at the back, meaning that the hydrogen is going to be in front. So we're moving from 1 to 2 to 3, is going in this direction. Now, since the fourth group is in front, it's supposed to be in the back. This was supposed to give us S configuration. Now we're going to swap it, it will still be R configuration. Why? Because the fourth group is in front. Shown below are Newman projections of 3,4 dichlorohexane. There is S, S, R, and R, S. Assign the correct configuration to each Newman projection. So here we're going to look at this carbon. You're also going to look at the carbon which is behind. Now, let's say your eye is a, remember there is this carbon and the carbon at the back, meaning there is a bond between those two carbons, right? So if you put your eye in this direction, what you basically see is you are going to see that bond between the carbon that is in front and the carbon that is behind. So I can write that carbon here and then that other carbon here. Okay, those two carbons. So if I look in this direction, these groups which are able to see this direction, you are going to see them as being behind you. Okay, so at carbon, this is the front carbon, this one. So it has got an hydrogen which is behind, and that hydrogen which is behind, remember, is down. So I'm going to put like this. This is hydrogen, and then this carbon which is behind, it also has an hydrogen behind, but it is more on, it's going on top like that. So I'm going to put it like this. And then there are these two chlorines which are in front if I look in that direction. Okay, so the first chlorine is in front on the first carbon. I'm going to put it like this because that's where my eyes are. And then for the other one, it is on top like this. And then the others which remain, which are up and down, those are just going to be along the plane. So we have got this one, which is a CH2, CH3. And then we have got, for the back carbon, we have got also this one, which is CH2, CH3. Now we can determine the RS configuration about each of these carbons. Which group is going to be number one? Chlorine will receive number one, and then after the chlorine, this is going to receive number two. This is going to receive number three. So this one is going like this. This is S configuration. So this is S. What of the other one? This is going to be number one. This will still be number two, and then this is going to be number three. Okay, like that. So we are moving like this. This is still S. So meaning that the first molecule is S, S. Okay, let me use this other one here. If I put again my eye in the same direction. I've placed my eye here, meaning I'm able to see the bond which is there. We are going to have a carbon here. Let me write Okay, should I write? Okay, let me write like that, and then I've got another carbon. These two chlorines, we are seeing them behind, but for the carbon which is in front, the chlorine is going to be down. The carbon which is behind, the chlorine is behind, but let me put it on top because this one is on top. And then for the carbon, sorry, I've put them on the same carbon. This one is for the carbon that is behind. Now, again, if I look in this direction, these two hydrogens are going to be in front. Okay, they're going to be in front if I look in that direction. Then what is going to be? How am I going to show that? For the first hydrogen, it's going to be like this. And then for the other one is pointed in the top direction to be like that. And then the other groups, for the back carbon, the CH2OH, CH2, CH3 is going to be down. For the one which is in front, the CH2, CH3 is going to be on top. Now considering this one, this is going to be carbon number 1, number 2 be here, number 3 will be here. So this is moving like this. Because if the hydrogen is in front, we're going to change configuration. So it's supposed to be S, so it's going to be R. And then this one, this is going to be number 1, number 2, number 3. Supposed to be S. But because the hydrogen is in front, we're going to swap, is going to be R. Meaning this is going to be R, comma R. Now, since this is S, comma S, this is R, comma R, definitely this is going to be R, comma S. We can determine that using the same way we've done. Which formula is meso compound? The meso compound has got both the R and S configuration, meaning that its uh, optical activity combined is going to be 0. You have got the same one in the same sample. One, let's say this molecule is supposed to be moving like that. In the same sample, one portion is pushing this plain polarized light to the right, another one to the left. Now, because they are in equal concentrations, you pull, you push, you pull, you push, they are going to be able to cancel each other. That's why the meso compounds, they've got an optical activity of 0. Which ones are enantiomers? These are enantiomers, which are simply mirror images of each other. Give a brief description of how a polarimeter works. Ensure you cover the following: the light source. Apart from the light source, you also want to cover the polarizer, you want to cover the sample, you also want to cover the data recorded. Now, here is a polarimeter which I've already written here. So you have got the source of light here, and then you have got this long tube. At the end, you have got where you're going to be reading from. Okay, that is the analyzer. That is at the end of the long tube. And then you have got this tube between here, which we call the polarimeter. Okay, tube. Now, at the beginning, we have got a fixed polarizer or simply a polarizer. Now, what is going to be happening is polarimeters are going to be measuring monochromatic light, meaning light of the same, only one color and one wavelength. So it's going to pass through two phases. The first plate is going to pass through is the polarimeter, and that one is going to be there to polarize the light, meaning that when light passes through this point, that light that is not of that doesn't polarize in the same way as the other light is going to be moved. So only the light that is able to polarize and be able to pass through this tube is going to pass. Anything else will not be able to pass through the polarizer. Okay. Now, as the light goes, it will start being rotated. As you can see, it was straight here. But as you can see, when it goes through the polarimeter tube, what happens? It starts to rotate like that. It starts to rotate and it starts to rotate. Depending on where there is S or there is the R isomer in the light source, it will depend with where it's going to rotate. Mostly the R rotates light to the right. Okay, and you are going to see with positive angles like that, but it's not always. And then the S, you are going to see with the negative angles. Okay, so at the end, it is going to hit the analyzer where you are going to be able to record or to analyze the light and read the angle. To find the angle that you are going to be able to get, you are going to remove from 90. So say 90 minus that angle that you get. Let's say you measure the angle like that, it's giving you 100. So that is going to be 90 minus 100 is going to give you that angle that you want. Now for here, I think it is already given where you're starting from. So whatever that you are going to be able to see, because light already started straight. So if it turns like this, the angle you get is going to